welcome to the ICI Game Changers seminar this week. It's the one before last this year. Today we'll be having a talk on space weather. And space weather is actually the subject that Maurizio Falanga, my colleague, covers. Unfortunately, he is ill today, and he asked me to replace him. It's my pleasure to introduce our speaker, Tamitha Skov, from the Aerospace Corporation in Los Angeles, California. I just heard that it's not sunny there, and we don't have the photons from the sun actually today, but usually of course, much more of that. She's also an adjunct professor at the Millersville University, and she works primarily in the fields of solar and space physics, and she tests spacecraft materials in realistic space radiation environments. She is doing a lot to popularize awareness of space weather, and she's also known as the space weather woman. So today we will hear from the space weather woman about the problem of forecasting geomagnetic storms, stealth CMEs, a new space weather extreme. As you wonder what CME stands for, these are coronal mass ejections. So Tamitha, it's our pleasure to have you here, and without further ado, I will give you the floor, and I'm looking forward to your talk.
Thank you, appreciate that. So for those who are expecting me to share slides, I will not share the screen because I like to stand in front of the slides and be able to show you and point to things and make it a little bit more interactive. So for those of you who are not familiar on Zoom, you can maximize me. So you don't have to look at me as a tiny little window. And you can either do that manually, or I think they might actually be doing that behind the scenes. They'll make me large. So feel free, you can pin me and make me big so that you can read what's going on the screen. And I think you'll enjoy it because there's a little bit of eye candy. Mauricio, when he asked me to give this talk, he wanted me to find a balance between the kind of the general interest and general science interest, and also have something in there for actual scientists who work in space weather. So I thought this might be a good topic, not just because we had an ICI team that was dealing with these problem geomagnetic storms, but also because it really shows how we are beginning to move the needle when it comes to doing forecasting, space weather forecasting for the public, and how that's actually beginning to cause this feedback loop back into the official agencies that have been doing space weather forecasting for a very long time. And the ICI team has been an integral part of that, showing how much we actually can change how we actually do space weather forecasting. So I'll share that with you. And before I begin, I want to make sure that I do give a special thanks to the entire ICI team. As you can see them here, I hopefully haven't left anyone's name out. And I will show a picture of them a little bit later, so you get to see get to be able to put a face with the names here. But these folks have been just kind of like an extended family over the past few years as we've worked to understand these stealth CMEs better. So to start off, I thought I'd start off simply. I know we were talking about CMEs. What is a CME? Well, we'll talk a little bit about that. And I will give you both the vernacular in the scientific community and also what is more of a layman's term vernacular. So for those of you who are non-experts, you may be technically minded, but you may not be experts to know all the jargon in the space weather field. Let me just kind of, level the floor a little bit for us all so that we can understand it. And then also for those who are space weather experts, you already know there's a ton of space weather. There's space weather everywhere. And really, in academia, we kind of lose sight of the fact that space weather actually affects Earth. And there's only a small fraction of that space weather that we really have to be concerned with. And in fact, there's only 4 basic types of space weather that affect life and society on Earth to any great measure. So let me explain a little bit what these are. And the first thing, obviously, that everybody knows are solar flares. And I'm playing an image of a solar flare right now. And you can see it right there. I'll go ahead and play it again. You can see it. It's this beautiful burst of light, electromagnetic light. You can see it right there. That's like an X-class flare. And this is what we call when the sun screams, because what happens here is where you get electromagnetic energy being shot out, burst very quickly. And this can have implications not just with causing ionization in the upper atmosphere, which then affects radio communications. But we can also have radio bursts. And these radio bursts actually go up to frequencies that are high enough when the sun is literally screaming that it can block out things like GPS signals. So I oftentimes call it like the difference between a cricket and a train, right? You can hear a cricket chirping all the time, even if they're next to a set of train tracks, if the train isn't coming. But if the train goes by, that cricket very well may be chirping, but you can't hear it until that train screams by and then disappears. Well, it's the same kind of idea with the sun. The cricket are oftentimes the satellites in the sky, right? And we can hear and receive their radio signals as long as that train, which is the sun, isn't screaming. When it flares, that's when it screams. And that's when you can't hear the cricket. The cricket's not being damaged or anything, right? The cricket's still chirping quite happily. It's just that receivers on the ground can't understand or can't pick it up because it's drowned out by the noise that the sun is making. So that's one of the biggest issues with solar flares, okay? The other big phenomena that everybody knows about, but usually conflate with solar flares, are solar storms. These are coronal mass ejections. And you can see that big loop coming out. I froze it so you can see it's a big loop. That's on the actual sun itself. But as you look past this and the picture continues, you can see there's the sun now. Now we're looking further out in what are called coronagraphs. And I'll talk about what coronagraphs are here more in a minute. But if you notice, as this big coronal mass ejection continues to move out in what is now called the solar wind, I'll freeze this picture here so you can see. You can see the legs of this thing are still sticking out of the sun. So it's still connected to the sun, if you notice, coming out in kind of like an arc like this. I do it the opposite way. It should be like this. But you can also see that it's still got this loop, that same kind of loop. And thank goodness for that loop. And some of you who are really savvy, you can see it actually almost looks like a tube. That tube or that loop actually is a magnetic configuration. And thank goodness for that, because that configuration stays reasonably robust even as it transits out to Earth. And it helps scientists understand a little bit more about the structure of these things. Thank goodness it doesn't get completely destroyed. Otherwise, we'd have no hope of being able to judge something that we see at the sun and then measure what we actually end up seeing at Earth, because it would be just completely, distorted or whatever. We still have problems with that, but it's not quite so bad. Thank goodness to this magnetic field that keeps it reasonably coherent. But solar storms, these are the structures that when they hit Earth, they're moving a lot more slowly than light, right? It's not, these don't move at the speed of light. It's a lot slower. It takes about 3 to 5 days to reach Earth. These take 8 minutes. But this stuff here, when this hits Earth, this causes a whole mess of problems, including aurora. But it also can cause radio propagation issues. So we still have some of the same things, but now we have issues out in space as well. We have satellites that can get damaged by this stuff because you can get them charged up and give them total dose increments. And so it's a problem for the health and safety of not just space assets, but also humans. And as we become into this space tourism era, and as we become this spacefaring race, and Elon Musk is quickly getting us out there, these types of things are becoming more and more of an issue for us. Now, as I move on, we've got solar flares and solar storms. They happen they can occur at the sun nearly simultaneously, but they don't hit Earth simultaneously. And so that's a problem for us when it comes to space weather forecasting in the public sphere, because these two in the public sphere are still conflated as being the same thing. We used to do that as scientists until Jack Gosling came along and set us all straight with the solar flare myth. But, and that's, other people could help too. It's not just Jack, but I have a tendency to give him credit for it. But in the public sphere, we haven't taken the public along with us. So that becomes still a problem. Now, to make things even more complicated, you have 2 different types of phenomena from the sun that actually create the third, or essentially cause the third to hit Earth. And that's solar radiation storms. And you can actually see one here in the coronagraph. That coronagraph looks pretty nasty, doesn't it? What happened to it? Well, it usually looks like this. And you can see all these little transient things being blown out. And I'll talk about those more in the next slide. But in just a moment, you'll see as we get close to Halloween, you'll see here very quickly that something really crazy happens. And I'll try to freeze it. Well, I'll let one go by. You start seeing snow kind of picking up on this thing in just a sec. There's a little bit. And now watch, here comes a big one. Boom, right there. See that? That's a blizzard. And I'll try to stop it at another. I think we've got one more coming on the 4th, and I'll try to stop it there so you can see. So this blizzard, whoops, Okay, I didn't get quite as well as I'd like. There we go. That's good enough of a blizzard. So this blizzard actually is energetic particles. And these are relativistic particles that are accelerated both by the solar flare and the solar storm when they're launched, the CME when they're launched. And these structures, actually, these particles, actually, not only do they cause issues for, let's say, optics and imagers out in space, because they actually cause these streaks. Because they literally penetrate the part into the electronics, into the detectors, and cause false, obviously false tracks, false images in light streaks. But they also, when they penetrate into the upper atmosphere, especially at high latitudes, you can see here the map of the world here, they're actually lighting up in a sense, they're ionizing a layer of the upper atmosphere. And that causes issues for, again, navigation through GPS or any type of GNSS service and radio communications, especially at obviously at high latitudes, because that's how it penetrates here at the planet. So that's another issue that is a real problem for us at Earth. And these things have a tendency, they last. They start essentially when the solar flare hits Earth, maybe about an hour later, and then they'll continue. If there happens to be a solar storm launch, they continue all the way through the period until this solar storm hits Earth, and then they begin to die down. So this can be days that you're dealing with this. And that's a real problem for things like airlines who have a lot of polar routes, for example, and maritime, Navy, drone reconnaissance, all sorts of different industries have problems with this. Now, the last one are coronal holes. And here you're looking at an image of the sun. And yes, it looks like, we're peeling the layer of an orange or something, that there's actually a hole that's being exposed. No, no, no. This is a name that's a pet name, but it actually isn't a hole. This is just showing that in this particular wavelength of light, the sun's corona or chromosphere is actually a bit dimmer, meaning cold. It's not emitting light in this particular frequency. It doesn't mean there's really a hole there. But what we do see is that from these coronal holes, we have cold, fast solar wind that comes out. And that fast solar wind, when it slams into slow solar wind ahead of it, actually mimics similar impacts at Earth that a solar storm would cause. So you can get aurora from these structures as well as other types of radio communication disruptions and things like that. So these are the basic 4 types of phenomena that affect Earth. And we're going to be talking mainly about this one here. But the one that we're going to talk about, imagine taking most of these signatures away and you can't see them at all. So that's one of the things, if you can't predict this, which is one of the most impactful of all of the space weather events, imagine how blind you'd be and how much that could disrupt society. And I'll talk a little bit about those impacts. Whoops. Let's see, can I move forward, please? Thank you. So now talking about coronagraphs a little bit more carefully. This is that same movie that I was talking about before. I'll just let it play this time so you can watch all the Halloween storms. It's kind of fun. But white light coronagraphs, they basically view very far beyond the corona and into the solar wind. And I'm putting this up so you can, because we're going to show them a little bit more. And so you can see the occulting disk here, and that's this area that's blocked out. You can see the sun in the center that we've just shown where the sun is. There's a blizzard. And then you've got the occulting disk here that blocks out the sun so that you can see all the dim structures that come out. And you can see all of these transients that come out. Some of them are what we call halo CMEs, which are the things that actually go all the way around. They make what we call like a halo, like an angel, thing that goes all the way around the sun. In this case, you can go up to about 30 solar radii. This is from LASCO on SOHO. This is from the Earth's view, okay? And these things are critical for viewing and forecasting CMEs. I'm going to pause this for just a second. These are critical for viewing and forecasting geomagnetic storms at Earth with halo CMEs, mainly because you can watch these structures coming out and you can gauge how fast they're moving. You can gauge the direction they're moving, whether they're going to hit Earth or not. They're very critical, especially viewed from the Earth, but also as viewed from the side. And that's where I'm going to start this. When you view them from the side, it's called a quadrature view. Sorry, and you see this disembodied hand out here. It's called quadrature, okay? And that's what you're looking at here. Now, this isn't exactly a chronograph. It's an imager, but it's on stereo. It's the heliospheric imager. But you can see how important it is to have something where you're viewing the sun from the side and you're watching structures that can propagate all the way across and hit something over here, okay? That view is called quadrature. It's basically from the side, and it can reveal a lot more dim images than you would normally see with an Earth-directed view, because Earth-directed view, something's coming out at you, and sure, it may make a halo, but as it moves out, it becomes even more dim. But let me play that again just for fun. Okay, so keep that in mind. We will talk about quadrature. That becomes very important when it comes to looking at stealth CMEs, because these structures are oftentimes so dim that the only way you can see them is in quadrature view. So one thing that is well known in the space weather community is the CME Transit Problem, right? This is often called the holy grail of space weather forecasting. Because solar phenomena really are just the first link in a chain of events as something comes to Earth, once a CME erupts from the sun, we can't a priori tell whether or not it's going to cause a storm at Earth. We can guess, but it's kind of like the terrestrial meteorological equivalent would be looking at this, looking at a hurricane being, forming in the Atlantic, for example, and then not having a clue, not having any satellite imagery from that point where it forms to know where it's going to hit and how well, not just where, but how strong is it going to be. And that's exactly where we are when it comes to space weather forecasting. We're basically back in the 60s trying to forecast these structures with basically no tracking up until we get right ahead of Earth. Okay, so that in of itself, not knowing the direction, the track, and all that kind of, and the distortion one of these structures incurs as it comes out to Earth, that's one part of the problem. The other major shortcoming in this CME transit problem is not knowing the magnetic field of this structure. And this is where the holy grail comes in, because everything in space weather is dominated by magnetic fields. So if you have a magnetic structure coming out, you want it to be able to have exactly the opposite polarity of the Earth's magnetic shield, because the Earth has its own, protective, well, we call it the magnetosphere for those who are in the know. But this magnetic shield has a field that points northward, essentially, if you toward the North Pole out here in front, which is really critical, because if you have a coronal mass ejection with southward pointing field, then those two fields, just like fridge magnets, if you ever put two fridge magnets together, if they're oriented the same way, with their fields pointing the same direction, they will repel one another. But if you flip one over, they'll click. And then these two separate magnetic systems become one system. And you can pump all of the energy from one system into the other. And that's when we get a geomagnetic storm at Earth. Okay, so that's the thing we can't predict at all with any fidelity whatsoever, partly because these things get distorted on their way out, and partly because we don't really always know the magnetic field that's coming out, because we can't visualize it. We know where the particles are, but we don't necessarily know what the field is doing. So really, we have real-time monitoring, including some satellite data up, at the head of Earth, what we call L1 position, which is out here in front of the bow shock, actually. So we can actually see this stuff coming in, but that only gives us like half an hour to an hour lead time. And that's really not enough. And on top of that, it's woefully inadequate for, let's say, public dissemination of space weather, because this stuff is non-trivial to look at. You kind of have to have a scientist in the loop or a meteorologist in the loop to interpret the data in real time and give updates on the ICME, the coronal mass ejection, CME. I means interplanetary. So now it's not a CME on the sun, it's something in the solar wind that's coming at us. That's all the I means. Sorry, I didn't define that. But updates on that arrival, and then implications for what type of impacts we're having on society at that time in terms of the different technological infrastructures. And really, academia has been extremely disassociated from the impacts. I mean, we talk about broader impacts in our proposals, and we see effects when we look at different articles that are written, typically space weather forensics, things that have happened decades, sometimes decades afterward. But we don't really look at it in real time and see the pain that space weather causes people in real time. And believe it or not, there's a lot more of it than we might have a clue about, to be honest. If I had to be honest, I was blindsided, and that was about 7 years ago, when I found out how many people were already paying attention to space weather because it affected them on the daily. I never anticipated I would find that, but believe it or not, it's pretty widespread. And here's the thing: social media offers insight into this real world of impacts. And that can greatly enhance our forecasting, not just as operational forecasters, but also in the academic world, because it can help us validate our models and validate our research and give us accountability and force us to be held accountable for the right and the wrong answer, which is something that space weather has kind of suffered from for a long time, being stuck in academia. And right now it's a resource that's currently underutilized. It's been utilized a little bit, and it's becoming more popular as more scientists jump on and go, wow, this is really helping me. and I'm loving that, because I think we're actually beginning to shift how people see space weather, both in academia and in the operational world. And they're seeing that there is a much larger need for space weather to be in the public eye than they ever had anticipated. So now let's talk about the stealthy CME prediction problem. Okay, this is, and I'm going to talk about this problem from the perspective of an actual event, because I think it's the easiest way to talk about it. In essence, the rest of the talk is going to be actually explaining the stealthy CME, what stealthy CMEs are. So this is an example of one of just many stealth CMEs. And I'm going to play this and see, you tell me, if you guys are now experts on identifying coronal mass ejections. You tell me if you see that stealthy CME launch right here. Ready? There it was. Did you see it? No? Should I try it again? This time, take a look here before and after. Take a look at this coronal hole that you could see. Remember, these are the holes, the dark stuff. Take a look at this and I'll show it to you again. Ready? There it goes. You see it? Hopefully you did. You saw the difference between this and this. That was a stealthy CME launch that Nariaki Nita and I saw in real time, because we were on social media at the time. And what we really saw was this slight partial halo coming out of this coronagraph, but we couldn't find a solar source at first. So we went back and scoured and scoured and scoured. And while we were scouring, we found this little coronal mass ejection thing. And it was so weak, we thought, how in the world could it cause, first of all, a halo at all, or even a partial halo? And then we just kind of panned it as being nothing. But when it actually hit Earth, it actually caused what we call a G3 level solar storm. Now, for those of you who are not familiar with KP, it's an index that measures the amount of magnetic movement, basically the disturbance level of at mid latitudes. And it's a nice space weather proxy. It's kind of rough, but it's a nice proxy to give us an idea of the impact. And in this case, it's a stoplight chart. You don't have to worry about the levels necessarily. Just know green is good, yellow is and red is storm. Okay. And in this case, it jumped to a moderate level storm, way above storm level, which was very surprising to us considering the weakness of the signatures we were seeing. So these weak events, we realized these weak events that are very stealthy could actually be very geoeffective. And this is a bad thing. As a matter of fact, I actually was approached by some people at Johnson Space Center when I gave a talk at COSPAR a few years ago. And they had said, we need a list of these events. And I was like, why? And they said, well, because we can't have astronauts doing EVA, out doing spacewalks when solar storms, when these CMEs hit, especially if they're going to be at G3 level, because we get spacecraft charging, right? And so the whole ISS charges up, and it can actually shock the astronauts. And that can actually make the astronauts extremely vulnerable, right? They've come in, some of these astronauts they were talking about have come in with their hands completely numb and worse. They've had worse, but you can imagine it could be a very life-threatening situation if someone were to, let's say, pardon my language, vomit in their spacesuit, right? You can't wipe that stuff out. You can't, how do you deal with it? Here on Earth, okay, you clean yourself up, you're fine. But here you're in a spacesuit and you're out doing a spacewalk. Suddenly this becomes a life-threatening event very, very quickly. And you're in 0G. So I don't even want to give you a visual for that. But so this became, a wake-up call for me that, oh my gosh, stealth CMEs are a problem. And as long as we continue to move out into, the commercial space era, and we don't have a handle on this on forecasting these types of events, so we can have a problem geomagnetic storm that causes a G3 level. This is not acceptable, right? So that began a quest of about that was back in 2015, and it's what now 2022. And so it kind of began a quest for stealth CMEs in both from doing NASA proposals and doing ICI proposals. And Nariaki and I started rediscovering stealth CMEs because they've been suspected to exist for decades, since about the days of Skylab. And to give you a rough definition of what stealth CMEs are, well, they're slow eruptions that occur typically high in the solar atmosphere, which renders them nearly invisible to detection. There really isn't an on-disk signature in the low corona. Sometimes there's not even a halo CME signature as well. And when they're visible, they're typically narrow structures in quadrature. Remember I talked about quadrature? And that's in with stereo observations, for example. And there's a fuzzy line between stealth and stealth-like as we began to really dig into them, because if we modify our observation techniques, we begin to pick them out, right? And that was likely part of a continuum of structures, and that was mentioned by Howard and Harrison back in 2013. And so why do we care? Well, I just showed you an example of why we care, right? Especially from a societal point of view. I mean, it's probably more important to society than it is to scientists necessarily, because they're pretty weak structures. What can we learn from them? Well, honestly, there's been a lot of work done on them. Wang et al. Found that you can't even observe 16% of all LASCO front-sided CMEs. Ma et al. Found that a third of all CMEs were stealthy or stealth-like. Diois found 40 events from 2012 with a very strict definition of basically no on-disk signatures, even on the limb. So these things can be extremely stealthy, and they're very frequent. And plus, under certain circumstances, they can be extremely geoeffective. And here's a couple papers on that. And Amelia is part of our ICI team, as a matter of fact. So these storms are frequent. And when we can't predict them, they're called in the magnetospheric community a problem geomagnetic storm. And these are going to plague us going forward. So it's not just the extreme events that hit really hard. It's also the events we can't see, these ninja CMEs. So once more, a little bit of a review. Just for those of you who are not experts, I just want to remind you or let you know what on-disk signatures really mean. There's typically multiple ways of seeing an on-disk signature. You can have a filament eruption where you actually are seeing material launching off of the sun. You can have what we call dimmings, where part of in the EUV wavelengths, you can see structures going dark like this. And you can also have a post-eruption arcade, which is kind of blurred out here, but you can see it quite well in this image. Okay, so you can see post-eruption arcades. They brighten after this coronal mass ejection left. As a matter of fact, you can see dimmings here too. So here's a before. You can see that filament, and then after. Okay, and then you can also get these sigmoids, right? These S's, and you can actually see a little bit of that S here and here, right? So you can see these things launch. And of course, solar flares are good on-disk signatures. I mean, there's all sorts of ways of seeing these structures typically. But what happens when there aren't on-disk signatures, right? Well, then you typically go to chronographs, right? I mean, oftentimes we look at chronographs first, or you'll see them typically in a chronograph. But the problem is, even though chronographs do provide a critical view, they're only part of the story. So here's an examples, 3 different examples of chronograph and on-disk signatures, right? So you can see, for instance, when you get a chronograph image like this is something that's coming out kind of southwest, and you can actually see on the front side, it reveals the source signature, the source region on the sun. And it's a front side, right? And from on-disk and chronographs together. Here's one that shows, almost a full halo, pretty much a full halo. And again, you have a nice image of on-disk signature with a nice EIT wave probably. And you can see that, as being a front side, CME, solar storm launch. But what happens when you get something like this? Well, we used to think, oh, well, that's far-sighted, right? Because with coronagraphs, you can get a big halo, but you don't know if that halo is coming towards you or if that halo is moving away. It could be behind you, behind the sun, and it's eruption on the backside, or the far side, rather. Sorry. Slap my hand for saying backside. I'm a very American, and we don't look at that as a vulgar term, but I'm trying to correct myself. But really, in this new paradigm, we don't necessarily know. I mean, granted, we've got a little bit of a signature here that gives us an indication that it's a far-sighted eruption, but we couldn't say for certain in this era of stealth CMEs that something like this might not actually be a stealth CME. So is it a far-sighted or stealth CME? What do you do when you can't distinguish a far-sighted eruption from a stealthy CME? Well, you put together a team. This is the ICI team. And there are a few people not shown. I apologize for that. But and I'm sure if there's any ICI people watching, they're like, oh no, why does she show that photograph? And for the human interest story. So you see Andre, you see Dana, here's Nariaki. He wrote the proposal and got us all together. You see Luciano, Jens, Erica, Ben, Stephanie, Paolo, Jennifer, myself, and then Ian. And then of course, we've got a few here who weren't able to join us for this particular meeting. But we do have a personal interest story, because if you notice the two in the back, see these two? You wonder why they're so close together. These two were not married at the time. As a matter of fact, they didn't even know each other prior to ISI. These two are now married, and it's all because of this man right here. He got them all together, and now Ben and Erica are now happily married, and hopefully studying, completely dedicated to stealth CMEs. That's all they're going to do for the rest of their lives, right? No, we'll see. But at any rate, the funny thing is that the closest we have in this whole group to a magnetospheric physicist is me, which is frightening because I'm not really. But working at the Aerospace Corporation, I do have some knowledge in magnetospheric physics. So problem geomagnetic storms, I kind of had to keep all of these solar and interplanetary people kind of grounded. And it was actually a lot of fun, because it really helped us to understand just even the societal impact of this stuff, with all of these different minds working on it, from modeling and solar observations to even interplanetary and high-speed stream expertise. And we'll talk a little bit more about that. So how do we know when we have a stealth CME? Well, there are typically two steps to trace an ICME, right? There's that I again. So this is an interplanetary CME. We often call them orphan CMEs, when we can't find a solar source region at first. And so I'm not going to explain what all this solar wind stuff is, but when we see one of these in ahead of Earth at L1, let's say, just ahead of Earth, we typically go back and we look in a particular time window, knowing the speed of this structure. We look back in a typical time window to Earth-directed, usually Earth view chronographs. And so you've got, here's the C2 and the C3 field of view, kind of looking in difference images for a particular coronal mass ejection. And then once we get that in the coronagraph images, then we can start looking for low disk signatures. And oftentimes, I mean, oops, oh, it didn't. Oh, that's strange. Oh, I should have shown it here. That's why I had it linked at the wrong place. So typically, for a typical coronal mass ejection, you're going to have something like this. And I always love showing Nariaki's picture, because you typically have, you know, a big solar flare, there's these big extreme events, and a huge EIT wave. You see, I mean, you know, who could miss this on disk signature, right? This is from the massive flare back in 2017 that fired a solar storm actually away from Earth, but then it actually hit Earth. It was such a massive thing. It was a near Carrington class event. And, you know, so it's legendary. But when you have extreme events like this, no one worries about whether or not you can detect them. They're very easy to detect. But when you have structures that don't give you an on-disk signature, well, this means that suddenly you have a stealth CME. And you have to modify your methods of detection to identify them. And that was one of the main goals of the ISI team, was to be able to figure out what exactly you needed to modify. And as a matter of fact, Erica published a paper, which I'll point you to later, that goes into that in great detail. And so during all of this meeting and stuff that we were doing during the ISI meetings, it was actually during solar minimum. And so we actually had stealth CMEs being launched all the time that we were actually doing our work. And it was neat because we were actually able to look at events in real time and add them to our master list as they were occurring, and then waiting and seeing how they would end up impacting Earth. So it was a really neat way of doing research, one that I've never done before, where you're actually integrating real-time events as they happen. And what it made us realize is that there are many observations of stealth CMEs in the current solar cycle, and that these structures seem to be on the rise during these low activity cycles, right? Cycle 24 was a low activity cycle. It looks like cycle 25 might be a low activity cycle. It's hard to tell, but the longer it takes for it to really ramp up, the bigger chance it has of being a cycle just like cycle 24 was. And so we're expected to have these stealth CMEs comprise a significant fraction over this new cycle. And what we started learning, again, I've mentioned it before, but many of these so-called stealth CMEs are only stealth-like. And Nariaki and I mentioned this in the paper back in 2017, and other people have mentioned it since. One thing that we did start noticing was that stealth CME eruption mechanics may actually be dynamically coupled to nearby coronal holes in many instances, not everyone, but in many instances. And I'll talk about that because I'll show you a couple other videos of these movies of these structures. But you saw that in that January 3rd event, right? That was that stealth CME that you saw launch was right at the edge of a coronal hole. And because of that, you can have interactions between stealth CMEs and high-speed streams. And these are the ones that have a potential to be most geoeffective. And I'll talk about high-speed streams in a second. But high-speed streams do vary dramatically over the course of a solar cycle. And so there may be a solar cycle dependence. The problem is that solar cycles, high-speed streams, let me rephrase that. The stealth CME detection is hard. It's very difficult during solar maximum because there's so many other events going on. And so, and not only that, but when we have spacecraft that are always moving, like stereo, they're always moving and changing their orientation and their view relative to Earth, view of the sun relative to Earth. And that causes other added difficulties in the observational geometries, because sometimes certain orientations, like being in quadrature, it's much more conducive to identifying and detecting these ninja CMEs compared to if they're not located behind the sun or at the same view as Earth, which is where stereo is now. So it's hard to get unbiased data sets, long-term data sets. And that's really what we're having when we want to look at solar cycle dependencies of stealth CMEs. We're having a problem with that right now, and I'm not sure we're going to be able to solve that anytime soon. But it's a worthy thing to look for, is the solar cycle dependence of stealth CMEs. So let me show you a couple, and these are smaller movies, but let me see if you can see the stealth CME that caused this eruption in the coronagraph. Whoop. Come on, play. So I'll tell you when it launches. Right there. Do you see it? It's at the bottom of this coronal hole, right over here. I'll play it again. You can see it. Right there. See it launch? And it actually elongated this coronal hole. So once again, associated with the coronal hole. Here's another one. Ready? This one's harder. I won't point it out. Not that. Not there. There you go. Shall we see it again? When this came out, it's amazing that it had such an incredibly intense difference image in coronagraphs, and yet, whoops, when you look at the actual disk images, you just see lots of little puffs, but you never see a real, that isn't it. Neither is that. There it is. Unbelievable. And I'll talk about this event in just a minute. Okay, so let me talk a little bit about high-speed streams and how they affect stealth CMEs. So for those of you, this is again a review for those of you who are not familiar with high-speed streams, you're not an expert in this particular field. High-speed streams, they are formed by fast solar wind originating from coronal holes. And I talked about that, but how that works with the sun is that if you think of the sun's solar wind, and I'll go over to this image here. If you think of the sun, we're looking down at the sun from the North Pole, okay? And you're looking at this kind of pinwheel kind of configuration. If you think about one of those pinwheel sprinklers, right, that spins and it shoots out water, you ever notice that the water, they look like they come out in these spirals, in these spiral arms. And as a physicist, you know that that's not what happens. The water's shooting straight out from the nozzle. But because the nozzle is rotating, it then causes it to look like it's tracing out an arc. And in the solar wind, it's the same kind of idea. You have solar wind that is being shot out radially, shot out straight out from the sun. But when we look at the magnetic field configuration, that threads each one of these parcels, kind of like a spider web threads through things. It basically ends up tracing, because the sun is rotating, it ends up tracing out an arc. Okay, so that's what we're seeing here. And as the sun rotates, if you have a region of slow solar wind and then fast and then slow, you have these arcs that come out. This is all slow solar wind in here. This is fast solar wind in here, and then slow solar wind behind it. But just like a boat plowing through water and it creates this bow wave, If you have fast solar wind slamming into slow solar wind ahead of it, it's going to compress it and cause this bow wave to form. Well, this bow wave, this compression region, is what we call the stream interaction region. So an SIR or a CIR if you've seen it more than once, and it's called co-rotating, same kind of thing. Okay, so let me get out of the words so you can see. So the higher speed streams, just as I mentioned, higher speed streams are in lessly tight wound spiral, as you can see. These are the slow solar wind is actually tight, it's a tighter spiral, it curves more. The high speed wind doesn't curve as much. And you have these fast wind overtaking the slow wind in kind of this archy kind of fashion, okay? And that causes the stream interface between the two. And oftentimes you'll get forward and reverse shocks that form at the interface. The interfaces can get extremely complicated. But here's the thing, when you have stealth CMEs launching at the edges of coronal holes, well, that's at the boundary between slow solar wind and fast solar wind. Inside the coronal hole, you have fast solar wind. Outside, you have slow solar wind. So where are they launching? Well, right there. They're launching right in the interface of fast solar wind and slow solar wind. So what happens is that the stealth CMEs that are embedded in these interfaces, that can enhance their ability to cause geomagnetic storms. So it's not that we're seeing these storms wrong. They really are weak things launching from the sun. But when they get embedded in structures like this, it enhances them because it just compresses them. So they're like little ninja bombs. I know, I looked for a ninja emoji, I couldn't find it. So this is the best I could do. But that's what ends up happening and why these things can become this new kind of stealthy extreme, because it's not that they're working alone, they're working in concert with stream interaction regions. So we can begin to start looking at how the coronal hole geometry ends up affecting that. So when we think about stream interaction regions, if we start looking at the sun, we can talk about a coronal hole being the blue and a CME, let's say a stealth CME, launching at the edge of these coronal holes in different configurations, different locations and configurations on the sun. And what we're postulating, or what we've seen, is that these structures, when we look at the time series, here's a time series of time going up on that side, in the axis here is the velocity, so the speed. So you can see the speed of a structure, the ICME, can be fast wind and then it slows down, and then you get the high speed stream later. Okay, so that's what I'm talking about. So these cartoons are illustrating how the variation with respect to the Earth-Sun line in terms of the geometry of these structures and how they launch affects the geoeffective potential at Earth, essentially. Each geometry will result in a different interaction between the high speed stream, which is in blue, to the ICME that's in red. Okay, and then the green is the stream interaction region. So if you have a configuration like this where you have a CME launching here, well, that ICME is going to end up reaching Earth long before the high-speed stream does. And that stream interaction region really is not, it's not really enhancing much. It's enhancing the tail end of that ICME. So it's not really all that, it's not going to be that geoeffective. But you take that same configuration of a coronal hole on the sun, and you move it now to the mirror, to basically the center disk, and now you launch that ICME, still off to the west, what we call the west of the sun, or west of the coronal hole on the sun. You launch it now, suddenly now that ICME is not so far ahead of that high-speed stream, and they have a much stronger interaction region. So now that ICME gets enhanced, and this can actually be very geoeffective. So you can get one of those surprise problematic geomagnetic storms if you can't even see that ICME coming. And then now let's just reverse it. Let's just put the coronal hole on the opposite side and then have the ICME here. In this case, you'll actually have the fast solar wind hitting Earth before the ICME does. It'll be embedded in the structure. But either of these two ends up making for a very strong, a very geoeffective composite structure. Like I said, these ICMEs don't work alone. They work in concert with high-speed streams. So over here is actually an Enlil run where you're looking down at the sun's north pole, and these pinwheel arms are those stream interaction regions I just showed you, right? And here we go, we have an ICME right in here. This was actually a stealth CME. And sure enough, when we just look at the model of it, sadly in the Enlil model, it breaks the actual pinwheel arm. In real life, it doesn't really do that, but hydrodynamic codes, this code doesn't have magnetic forces, so it's not nearly as robust as one that would actually do the full solution. But it's still illustrative because you have the high speed stream, then you have an ICME, and then you have the high speed stream, which is basically this configuration. And when we go back and we look at solar observations of Earth, that's that's for that particular event. It looks very much like this. So let's take a look at a couple of these events. I'm just going to show you two of them. Here's that October event I was telling you about. And so you can see the solar, the raw images of the solar observations in 211 angstroms. This is before, this is after. And you're showing, you don't really see much of a change in the after picture where that CME launched. But if I put in the difference image, this is the base difference image. This is by modifying the techniques of observation. Suddenly, the dimming regions become much more apparent, right? And now you can see why those areas are circled. So the observed in situ, when we look at the in situ data, and I shouldn't go over this in too much detail, but when we actually look at it, we look at magnetic field. There's three components of the magnetic field. We've got the total magnetic field here. Again, time is moving to the right of this in this diagram. And you look at the strength of the magnetic field, you can see this enhancement all in through here. So this is the ICME region, okay? And sure enough, when we look at the velocity, it starts out slow. And of course, right in this region where the solar wind is beginning to speed up, that is the stream interaction region. And of course, we go up here to the high-speed stream. So this is in the front end of a high-speed stream. And in fact, if you look at it, look, there's the coronal hole right there. And this structure launched just to the south and to the west of this coronal hole, okay? Exactly this configuration right here, exactly what we would expect from our geometry, okay? So we have this stream interaction region right in here. And sure enough, we get a G3 level solar storm. Okay? And I don't think I have time to go over this, so I'm not going to go over this, but this, looking at the strahl electrons gives us an idea that what we're seeing is interchange reconnection, which is part and parcel of how we think the mechanism, part of the mechanism that is causing the eruptions here for these filaments as the coronal hole, as the fast wind from the coronal hole may actually be exerting a drag, kind of a drag, and kind of ripping these structures and causing them to go unstable and launch. So if I show now the inlow runs, you can actually see the ICME and the density. This is the density picture. This is the velocity picture. You can hardly see the ICME because the ICME is extremely slow. You can barely see it as an extension of this SIR, the fast solar wind that's coming in it. But you can actually see it much more here in the density. And sure enough, it's part of the stream interaction region. That's this pinwheel arm coming here. So the high-speed stream is really just behind it. I probably should put this arrow here because the high-speed stream is just slightly behind it. And the east flank of this ICME, you can see, is embedded in that density enhancement. And the western portion of it is convecting with the ambient solar wind ahead of the ICME. That's this here. Okay, that's that ambient part. And sure enough, this structure was enough to cause a geomagnetic storm at the G3 level. Now, taking a look back at our old friend, this is that January 3rd event you can see here. And when you look at it in the solar wind, and in this case, the problem that we have here is that this structure was much further south. So we actually just got grazed by this structure. We didn't really get it for very long. So it really isn't, it's center disk, but it's, it's moved down in latitude, and my images don't really show that very well. But you have a high-speed stream, an ICME embedded in a high-speed stream according to this. And in this case, because we're just getting clipped by the high-speed stream, when we look at our velocity, we're seeing a little bit of high-speed stream, but it's kind of ratty. And that's partly because we're just barely in it. Sure enough, here is the ICME embedded in this, and it's actually slower. So the high-speed stream is actually, it's actually accelerating this thing and compressing it a bit more. And again, once you get outside the ICME, again, you see this higher speed stream. So it really is embedded in the structure. And it's really not that strong. It's strong enough, but it did enhance the southward pointing field to almost 20 nanotesla. So we ended up having, and I don't want my labels disappeared. I had labels on this. Sorry about that. But the labels, I believe this is that G3 level storm, as you saw. And you can see DST goes down to -100. And so, yeah, as I mentioned, the solar wind speed enhancement is likely due to that high speed wind, but the signature is weak because, the high speed signature is weak because it's likely further south, and we're not getting it directly as if that coronal hole were, in the equatorial region for the Earth to see. Oh, and here's the difference image. My apologies. You can see the difference image here, where it clearly shows where that dimming is and where that coronal hole ended up getting elongated. And so you can see that a lot of this analysis in our 2017 paper. So the summary of the STEL CME problem is that they're a noteworthy aspect of space weather. They're really a new kind of stream event, and many of these eruptions occur at coronal hole boundaries that result in ICMEs bedded in high-speed streams. This basically stream interaction regions, which lead to very geoaffective composite events. We think they're on the rise during the low activity cycles, and there's likely a solar cycle dependence. So if you want to look at the modification of the observation schemes to see these structures, which are just slowly being picked up by social media, please look at the Palmario, Erica's paper in Frontiers. And it talks, in here she talks a lot about how to change these observation schemes and how much difference it makes. And then one of the things we haven't been studied very much in terms of these structures yet are eruptions near coronal hole boundaries. I mean, people talk about a lot of different things, filament channel, active regions, streamer blowouts, that kind of thing, but coronal hole boundaries have not been studied with any fidelity as of yet. And we actually talk about this in the review paper that's coming out right now, or that's been out for a few months now. So please take a look at that in Space Science Reviews. And that is all the work that that's a bulk of the work that we've done trying to identify STEL CMEs and look at the historical perspective and try to get a better handle on what they all entail. So why does this space weather forecasting matter? Well, it matters for all of these different stakeholders. So we have amateur radio operators. We have obviously the Aurora tourism industry, which is now exploding with things like Blue Origin, Virgin Galactic, SpaceX, right? We have the original players, which are like the FAA and the Department of Energy, Homeland Security, that type of thing. We have, the astronaut enthusiasts. We have media outlets. We have the other 3 billion people in the world that now need internet, right? Starlink is going up. And of course, the emerging drone industry, right, which uses GPS quite extensively. However, we have to return to the 60s when it comes to space weather forecasting relative to terrestrial meteorology. And really, it's because space weather forecasting was developed as a response to extreme events, not to STEL CMEs. We have lots of models that predict solar fields and transit, and we give alerts that, for ground-induced, geomagnetically induced currents during solar storms. We also get radio blackouts and radiation storms, which lead us to the alerts for the FAA, for airlines, for instance, during solar flares. And then we have, of course, ground telescopes and spacecraft telescopes. They're constantly staring at the sun. So you'd think that we'd have everything covered, but we really don't. We're very much like Harry Volkmann's 1960s version of weather. He was actually the first terrestrial meteorologist to do weather on television. And he was an amateur radio operator, and he basically took forecasts from the military bases and forecasts of tornadoes. And he actually put them on a map of Illinois and then told the public where there would be tornado warnings. And the military and a lot of other agencies at the time told him, you're going to incite a panic. And in actuality, he didn't. The public was very grateful because they felt much better informed. As a matter of fact, he got something like 1,600 letters to his station the very first time he did this. And Matt Parker, who was the deceased president of the American Meteorological Society, said, Tamitha, I feel that you're doing the same thing for space weather that Harry Volkmann did for terrestrial weather. And so that's actually helped me a lot, because it's helped me realize that there's a precedent set for this and that we can continue along the path, even though we get lots of arrows in our back for doing so, which, trust me, we do. But here's a perfect example. Now, this is not a STEL CME, but I'm going to show you something how we move the needle, and I'll try to hurry because I know we're getting short on time. During the back in 2017, when we had Irma barreling down on Puerto Rico, we also had a very nasty region 2673, that fired off the 2 largest solar flares of solar cycle 24. And in 1 week, region 2673 launched from September 3rd to September 10th, 4 X-class flares at what we call an R3 to R4 level radio blackout. Excuse me, I've got something in my throat. But the scales only go to 5. So when you see an R3 to an R4, that's pretty intense, right? You have 25, there were like 26 M-class flares at an R1 to R2 level radio blackout. So the sun was screaming like all the time. We had 2 radiation storms at an S2 to S3 level, and we had a geomagnetic storm. One of them was a G4 level. Again, the scales only go to 5. So when you see levels like 2, 3, 4, these are pretty intense. And this was happening all at once. And that's the thing with space weather events. They have a tendency to cluster. So we basically had some horrible thing with solar flares, radio blackouts, radiation storms, and geomagnetic storms happening all at once for an entire week. And this was when we needed amateur radio operators to be able to do emergency communications for the people decimated in Puerto Rico. Now, social media during this period, well, we had Aurora in New York. We had Aurora clear down to Arkansas, but I like this picture. This is from New York because it's just so beautiful. This was Brazilian TV. These were all being reported to me on social media. This is saying, I don't know if anybody reads it, can read it, but it's actually saying interferencia solar, meaning the sun was blocking out direct TV, so no one could even get a signal. This was the CW network. This is amateur radio, excuse me, again, amateur radio in Morse code. It's the most robust form of analog radio signals. And if I play it, you can actually watch. Here's the radio connect. Kill this now. Here's the radio connectivity. And you can actually see radio contacts being made all through here. But watch, as the big X8 flare hits, watch the radio communications just absolutely die. Do you see that? Nothing. There's absolutely nothing. And this is when Irma was right here. So imagine all the emergency responders that were doing hurricane watch nets, ARAs and RACEs and the ARRL, all these people trying to help people in the Florida Keys and know what was going on in these decimated areas. They couldn't communicate at all. The only reason why you got radio communication here was because it was on the sun's night side, the Earth's night side. If you can't see the sun, you can't hear it scream, but it absolutely decimates radio propagation for everyone else. And then my forecasts were even picked up by a Russian network. So this is me actually talking. They took it straight from my YouTube videos. You can actually see part of my logo right there. They lifted it and you can see my name in Russian, and then they actually had a Russian translator. And this is where I was talking about the radio propagation issues for the amateur radio operators. So this is what I'm hoping we'll get on network on regular television. It doesn't have to be me. It can be a local meteorologist talking space weather. But this is the kind of level of coverage that I think space weather needs. And then here's the final thing, right? Here's the reciprocity between social media and the community. We are now, believe it or not, we've grown quite extensively. There's a large number of space weather forecasters and subject matter experts accessible via social media. And we have thousands of local field reporters now. These include citizen scientists, technical engineers, space weather enthusiasts, and they all are giving us anecdotal real-time reports of what's going on in space weather, including radio propagation, GNSS issues. The community, just my community, is now over 100,000 on multiple social media platforms. And I'm just one of many, right? We're growing so fast. So this paradigm shift is actually picking up steam. It's creating an atmosphere of accountability that is challenging our academic and operational communities. And there's an evidence of heightened awareness of space weather and pop culture and responsivity even within government and space weather agencies. And I'll show that in just a second. Actually, I'll show it now. This is, I'll talk about this in a sec. I did a tweet here, a post. And I said, glad the Met Office is officially adopting the term stealth CME now. This is a testament to how proactive reporting on social media can lead to new science and ultimately move the needle when it comes to space weather forecasts and operation. A big thanks to those at the Met Office space, because sure enough, just a few months ago, they actually put in their official report, stealth CME. So ICI is moving the needle when it comes to big government agencies. And I find that fascinating and a real breath of fresh air. So this reciprocity is an ideal laboratory testbed for scientific model development, discussion, and research, right? It's not just for the public, it's for scientists, and it's also for industry. So please, if you, excuse me, if you are at all interested in, or if you are on social media, come join us. There's lots of different stuff that you can learn. There's accredited training now. I'm actually training in Millersville. I'm actually being asked to do even more training now, which is why I may actually not be long for aerospace, because this stuff is pulling me completely off of doing research, sadly, and more into training people. We have a lot of resources for those who are on social media, for both scientists and for the public. We also have amateur radio if you're looking for specialization for radio, not just HF, but UHF, VHF, all sorts of others. And then radiation. So people are picking up on radiation doses and dose rates and things like that, and there's lots of resources there as well. So please feel free to contact me. I am very, very easy to find. And thank you for your time.
Thank you very, very much, Tamitha, for this excellent and lively talk. Thank you very much. We're already past the hour, but I hope you have a little time for answering some questions.
Sure.
And you guys in the audience, you can use two ways of posing questions. You can either write in the chat, which some of you have already done, or you can raise your hand and speak for yourself. And when you write in the chat, I will try to summarize and read the question to Tamitha so she can answer them. So just picking up at near the end of your talk, there are two questions about catalogs of stealth CMEs, and there was mention of the Richardson, if I got that right, catalog. Are stealth CMEs listed there?
Stealth CMEs, stealth CMEs are being listed in the Richardson catalog. I don't know, you'd have to talk to Ian to see whether or not he's listed all of them. But we do have master lists. Some of them you can get access to, at least in our review paper, and you can contact us for more. But I do believe Ian is going to be, if he hasn't completely populated his catalog with all of the stealth CMEs, that will be done shortly. I don't want to speak for him, but I believe he is, yes. He will be pelted with olives if he's not.
Another question is, are all or most geoeffective stealth CMEs associated with corona holes?
The most geoeffective are. Not, I don't think all of them, and the problem is that, you know, with stealth CMEs, you get into this fuzzy area of stealth CME versus stealth-like. And so obviously when you start moving away from relationship with fast solar wind, then the stealth CMEs that are more geoeffective end up being more, you know, they become less stealthy because they become, you know, more, they become stronger events in of them their own right. And so you start getting into that argument. That's part of the problem, is when you have this continuum of structures, some people may say, yes, this qualifies as a stealth CME, and some people might say, no, I don't think that's really stealthy because I can see it. And so I don't think we've been able to land safely on a definitive answer in that regard, because I don't think, just simply because the boundaries of what is stealthy and what is not is so fuzzy. But I wouldn't rule it out. But I would say that I would qualify it by saying that those are stealth. The ones that don't require a little extra boost from a stream interaction region are likely only stealth-like and not completely stealthy.
Thank you. I should not forget to name the people that asked the question. So William Ball asks, can we see the effects in real time of solar storms on other celestial bodies like Venus, Mars, the moon, asteroids? Can that provide insights into space weather?
The issue with, obviously the issue with seeing things in real time, with stealth CMEs, I think it's extremely difficult. Mars obviously would be the one that we would have the most ghost of a chance of seeing that. But the problem is, I mean, and we even, that can even be said for regular CMEs as well, because when you're looking at the impacts, especially on the ground, you're going to have to be using the instruments that you have there. And with regular events, you know, that can actually drive, let's say, radiation storms, you know, solar, you know, SEPs, solar energetic particle events, you can actually measure that with, let's say, Curiosity on the ground and their rad detector. But when you're dealing with stealth CMEs, if you have some type of storm occurring, which, you know, and Mars is that's another issue in of itself, because they don't have a robust, you know, they don't have a magnetic dynamo, so the field is remnant. And it causes, you know, more local effects. The issue that you end up having with Mars is, for instance, radio propagation. When you have these big when you have storms that occur, you would see impacts in radio, in radio frequency, radio frequencies and radio communication issues. But that's kind of difficult when you don't have a lot of instruments that are designed to detect those types of problems. So I think we're a ways off from looking at real-time effects at other planets, maybe through orbiters, but that's kind of difficult. So I don't know. My perfunctory response would be no, that you probably can't right now at other celestial bodies. But that is definitely something we should look for in the future.
Okay, Chelsea makes the observation that there is apparently a relation between the terrestrial weather events and stealth weather events, and she asks for connections.
I'm sorry, I missed that. Connections between
interesting
stealth,
that it happens
CMEs and
during big terrestrial weather events. Connection.
Oh, right. Oh my goodness. Oh, that's a can of worms. Okay. It's an interesting can of worms, though. That's one of the things that I am particularly interested in, because there's a lot of fringe science being done on that right now. And of course, fringe science, as much as we love fringe scientists, they're not very robust in their methodologies. So we really need mainstream science to start picking that up. The problem that we have is that terrestrial meteorology, they're in a neutral regime, right? They don't understand the charged regime at all. So what we need are people who can be cross-disciplinary and study and have a knowledge of atmospheric chemistry, and especially even the neutral chemistry and the coupling between electromagnetic and the neutral regimes, and then also have some type of space weather expertise. Because if you only have ionospheric expertise, then you don't understand the events that are coming from our star, and you don't understand how they impact the magnetosphere and then into the ionosphere. And that's really, I think, what's slowing us down. But that is a paradigm I'm trying to change. Is I'm trying to get people who are who have terrestrial meteorology chops into having some level of space weather expertise and an understanding of the electromagnetic phenomena that occur, because there does seem to be coupling. There seems to be coupling through gravity waves, for example. Even from, we already know that there's coupling going up, but we think there's also coupling going down. So from the ionosphere, you can actually have the sporadic E layer, for example. I won't get into too deep a topic here, but you can have the sporadic E layer actually dumping its charge and dissipating through once you get gravity wave propagation up from, let's say, a storm, from a hurricane or something, into up to that level, up to that altitude where the sporadic E layer is. It changes the conductivity somehow. It lowers the threshold for some type of charge dissipation. And so you end up getting intensification of lightning. And we've seen studies where people are talking about that. You also get sprites that occur, and they think that that's something to do with the coupling between the electromagnetic regimes regions and layers in the ionosphere down to these neutral regions. And it looks like gravity waves are, at least that's the strong contender for the communication at this time. But I'm sure there's a lot more to it. And that's a field that really needs to be blown wide open by mainstream science, and it just hasn't yet. So yes, there's coupling, lightning intensifies. We're seeing sometimes wind intensifies in these storms, which probably has to do with their electromagnetic strength, right? With the intensity of the magnetic fields inside these structures. There's just all sorts of really interesting dynamics that have yet to be probed in a robust manner. So excellent question. I wish I had a better answer for you.
Okay, Rita asks about the likelihood of Carrington type events.
Oh my goodness, yes. Sadly, if anyone follows the McIntosh et al. Crew and NCAR and UCAR, you'll realize that during these low activity cycles, we're talking about solar hemispheric asymmetry, and that's something that a lot of the solar physics community doesn't really grapple with yet, and they really need to, because when we have these hemispheric asymmetries where the magnetic field of the northern hemisphere is different than the magnetic field of the southern hemisphere, meaning that they're out of phase in terms of the Schwabe cycle, let's say, which is an 11-year cycle. When they're out of phase like this, that means that we end up getting lower activity cycles overall magnetically, but the magnetic fields become extremely complicated. And so during activity cycles that are lower, like cycle 24, like possibly cycle 25, we have actually a higher incidence, a higher possibility or probability of getting Carrington class events, simply because it takes those really complex magnetic field configurations to cause very unstable and very extreme, the extreme of the extreme to be launched. So it's almost counterintuitive. You would think that the more active a cycle is, the bigger the chance for Carrington class events. That's not necessarily true. It's actually the more active the cycle is, the more extreme, the more frequent extreme events occur. But in the low activity phases or low activity cycles, then that's when you get the extreme of the extreme. And if there's still low probability events, but now you can get ones that are Carrington class. And so, for instance, in cycle 24, we saw at least 2, if not 3, I'll say 2.5 Carrington class events. The half being the one that was launched that I showed you, that X2 point flare back in 2017, that was actually launched to the far side of the sun, but it was wide enough that it actually clipped Earth and gave us a G1 level storm. I mean, it was unbelievable. The structure was easily 270 degrees, in full extent. And well, not quite, but close. And then it wasn't considered Carrington class because as the flank of it hit Earth, it wasn't moving quickly enough. But I argue with people like Chris Mostel that if we had actually seen the center of it, the apex instead of the flank, that it would have been moving fast enough to be considered Carrington class. And he threw his arms up and said, yeah, you may be right. But we didn't have stereo B at the time. And it went right past stereo B, and we're just frustrated that poor stereo B didn't make it. So we don't have any in situ observations of the apex of that storm. But that tells you, if you have 2 or maybe 3 Carrington class events during solar cycle 24, it's those low activity cycles that you really have to worry for. So I'm kind of hoping cycle 25 isn't one of those. Okay. Hopefully that answers the question.
Okay, Heidi Hamill picks up on the question of William Waltz and remarks that there are space weather effects observable or observed in the planets, like for instance, Aurora, Jupiter, so forth. Well, but she has a question. Will the Daniel K. Inouye solar telescope have any impact, or is its field of view too small? It certainly can aid with understanding polarization. Thoughts?
I have to stop short of that because I haven't had enough time to really dig into how that telescope is going to help us. In terms of operational space weather, I'm not sure. In terms of academia, there's a whole host of things that's going to help us do. So I sadly will defer that question probably for offline, so we can discuss it in more detail. But operationally, it's a nice to have. And we will see, as of yet, we will see what it will add operationally. I think academically, it's going to add a lot more first there. Polarization is not necessarily something that operational scientists, operational forecasters use. And so I don't have a good insight into that as of yet, but that's coming.
Okay, we have a raised hand now. Big Pizzo, is asking to get the floor and ask a question, and Willie would open the mic for him. Vic, please. No? You have to open your microphone.
Yeah, I do.
Okay.
So can you hear me now?
Just ask your question.
Yeah.
Can you hear me?
Yeah.
Okay. All right. Yeah. No. On regard to the stealth CMEs, we in the forecast business, we've been aware of these for a long time, and it happens for a number of reasons. Sometimes it's simply an operational situation where you get a change of shift, and the chronograph images come down, not in real time. They come down in bursts usually, and sometimes things get missed that way. Sometimes the sun is extremely active, and you'll miss a CME embedded in a bunch of other CMEs. But mostly, one of the things I think you need to emphasize was those really energetic events that you showed there. At the start, the really big CMEs in the 2017 class of CMEs and all. Those are not stealth CMEs and never will be. So what you're going to see is stealth CMEs are relatively weak CMEs. And they probably related mostly to streamer blowouts that occur high up in the atmosphere and therefore create almost no signature down low. And finally, I'll say our forecasters look at the chronograph images and make the forecast from that. And assuming you have 2 views, you don't miss too much that way. And it's rare that you kind of are going to miss anything. And then in the forecasts are based upon, our forecasts are based upon seeing these things in the coronagraph field of view. They're not based upon what you see at the surface. That is kind of supplementary information, but you're not going to make your forecast off of that. So
Yes.
anyway,
Thank you, Vic. I appreciate your input. Yeah, two things. First, I didn't mean to give any impression that the 2017 events were stealth CMEs. That was not the case at all. I was using that as an indicator of where I'm hoping that we'll end up going with space weather in terms of operational impacts in pop culture and in media. Those events were pretty intense, and it shows a clear need for space weather forecasting, especially during, inclement terrestrial weather events. And that's why I called it a perfect storm. So stealth CMEs may not necessarily do that, but as we have people in space, for example, doing EVAs or doing, space tourism or half a dozen other things that we will soon be doing with our budding commercial space industry growing as rapidly as it is, we need to be aware of all of these events. And as good as the Space Weather Prediction Center is and others are at forecasting, we have seen many times in social media a lot of punts, and that's what we call them, punts, where either the forecast is, the chronograph images are too complicated, so no one does a prediction, or they just flat out miss it. And granted, most of these structures do have some type of coronagraph image, but a lot of times the halos can be extremely light. And as a matter of fact, we have one right now. There is, and I just posted it on social media. So we have an event right now that Space Weather Prediction Center has not posted yet. I'm hoping they will. But if you look, it's a stealth CME, essentially a stealth CME. Well, no, it wasn't really stealth CME, it was a filament eruption. But the halo in the chronograph was so incredibly weak that that if you didn't know that there was an on-disk, signature, you would have missed the halo. And that's oftentimes what happens with these stealth CMEs, is that the halos themselves, even in difference images, are extremely weak. And if you're able to modify your on-disk imagery so that your observations, so that you're able to see these usually they take their long baseline imagery differences. So you have to take like a base difference image over sometimes as long as 16 to 24 hours, because these eruptions are extremely slow. So as long as you're willing to do that, which right now, that's not part of Space Weather Prediction Center standard operation and procedure, you may actually miss the halo. And we've seen that so many times in social media. For instance, that January 3rd event that I showed, that was never predicted, even though it had a halo, right? It looked like it was further south and there was no prediction made for it. And yet, if you go back to the on-disk imagery, you realize, oh, it was south, but it wasn't that far south. And so you might reassess whether or not you think something is going to be Earth directed based on what you see in the on-disk imagery, as opposed to what you just see in coronagraphs. So, Vic, you and I may banter offline about this, because I definitely have insight in this, doing it in real time over the last 7 years, that might surprise you. So it is definitely something that is still a work in progress, and I don't think you can just dismiss on-disk imagery, whether you have it or not, as being just a luxury. I think it is a critical component, especially when it comes to stealth CMEs. So hopefully that addresses that. But I respect your opinion.
I think we have to come to some closure, but let's have one last question. How can ICMEs in general can affect magnetic reconnection on Earth? Is there studies about that?
How can CMEs affect
magnetic reconnection on Earth? Are there studies about that?
Oh my goodness, yes, they're called, yeah. Maybe I'm misunderstanding the question, but that's the fundamental, the biggest type of reconnection that occurs at Earth is based on coronal mass ejections hitting Earth and causing a dramatic reconfiguration. That is what a geomagnetic storm is. Of course, small stealth CMEs may not drive reconnection to that level. And there's a lot of argument as to whether or not you can have things like northward turnings and all of this other stuff with substorm dynamics. Is that simply a reconfiguration of Earth's magnetic field all on its own, or is it driven at all by the solar wind? and structures in the solar wind. And that's a whole nother topic. But yes, I mean, CMEs dramatically affect reconfiguration of Earth's magnetic field. And that is really the number one reason why you have geomagnetically induced currents on the ground. It is the reason why you have aurora. That is that whole process. So, you know, arguably the bulk of space weather papers on reconnection at Earth have something to do with CMEs.
Okay, yeah, thank you very much. I think this is a good closure. Thank you very much again for your interesting and lively talk. And I would just like to point out that next week we're changing gears again. We're turning to life in the subsurface. Barbara Sherwood-Luller will give a lecture on life in the subsurface of the Earth and the planets. You're invited to join us again next Thursday at the same time. And until then, you have a good week. And Tamitha, again, thank you very, very much. This was excellent. Thank you.
Wonderful. Thank you so much. I appreciate
Bye-bye.
it. Thanks for the wonderful questions too, everyone.